Recording in progress.
In continuation with the last class, we'll see the different shapes of molecules we are now going to see. Let me share the screen to you. Okay, so how the bonds are formed and how the shapes of the molecules, the VSEPR theory is conforming. We saw, right, based on the total number of VSEPs and number of bond pairs. Okay, number of, so we saw until number of bond pairs. Right now, we are going to see molecules containing both bond pairs and lone pair. Okay, so first type we'll see AB to E. So A is the central atom and B is bond pairs. Number of bond pair is 2 and 1 lone pair. So we are going to see two bond pairs and 1 lone pair. So it forms, it is bent, right? The shape is bent. And then the famous example, we saw already ozone, right? Ozone is an example for this, and SO2, these are all the example. Okay. Then AB3E means one central atom. There are 4 VSEPs. Before that, we saw AB2E type, right? So this also you can able to see. First, what we saw, this one and this one. These two are the bond pair. Okay, this one is the lone pair we saw. So how many VSEPs now? 1, 2, 3. 3 VSEPs. So the shape is bent. Okay. And then the electron geometry is trigonal planar. Right? Or we can say it is triangular. Yeah, it is a planar only. Trigonal planar. Okay. Example, ozone and SO2 we can say. Okay. Show bond angles also. The angle is 120 degree in between these two. Between these two, it is here. In between these two, this is also 120 degree. Okay. Then we'll see AB3E type. AB3. So a bond pair is 3 and 1 lone pair. See 1, 2, 3. 1, 2, 3 bond pair and 1 lone pair. Right? Clear? So what is the type we had to see? It is trigonal pyramidal. Example is NH3, we can say. Electron geometry is tetrahedral. So electron geometry is different from molecular geometry. Electrons geometry I'm talking about, it is tetrahedral. Molecular geometry is trigonal bipyramidal. Okay, the angle is 109.5 degree. Then here 4 VSEPs available. Suppose if you are taking, it is AB3E. Suppose if you are taking AB2E2. So two bond pairs and 2 lone pairs. Okay. So this one, if you're taking this, the molecular geometry is bent and the electron geometry, as usual, it is tetrahedral. Can you able to understand this? The famous example is water. Water is its example. Then AB4E, we can say. After AB3E, what we saw for AB3E, NH3. Then we saw AB2E2, that is H2O. Now we are going to see AB4E. So first we saw 3 VSEPs and 4 VSEPs. 4 VSEPs, 2 categories, AB3E and AB2E2. Okay. And then you know the number of bond pairs and number of lone pairs. Now we are going to see AB4E. In AB4E, how many VSEPs are there? Valence electron pairs? 5. Okay. So AB4E. So 1E, 1 lone pair, then AB4, this one. So 1, 2, 3, and 4. Okay, 1, 2, 3, 4. Clear? So 120 degree, 90 degree it consists of. So 4 bond pair and 1 lone pair. So 5 VSEPs. Okay, it is like a seesaw. The molecular geometry is like a seesaw, and the electron geometry is trigonal bipyramidal. Can you able to understand? It is. The famous example is SF4. Okay, that is the famous example. SF4. Okay, clear? Then we'll see now AB3E2. That is also having, okay, AB3E2. So AB3E2 also having how many VSEPs? 5 VSEPs. See, 1, 2, 3 bond pairs and 2 lone pairs. Clear? So all 90-degree it is. It is actually T-shaped. See, this one is like a T-shaped. Listen to this. It is a T shape, like a T. Hmm? It is a T-shaped, the molecular geometry, but electronic geometry is trigonal bipyramidal only. And example, actually, here we can say, what is an example? Let me check with an example. Okay. T-shaped. For T-shaped, what is an example? I'll give you the example at the last. Let me check with an example and give you. Then AB5E, that is having 6 VSEPs, that is 5 bond pairs and 1 lone pair. Say, for example, 5 bond pairs. 5 bond pairs and 1 lone pair. The shape is square pyramid. Okay. Here we can say bromine and F5. Similarly, we can say for T-shaped. So before that we saw, right, T-shaped is AB3E2. That is AB3E2. That is T-shaped. For example, Cl and F3. Chlorine, F3. For a square pyramid, 5. Okay. So 5 bond pair. 1, 2, 3, 4, 5. 5 bond pair and 1 lone pair. So it is square pyramid. Totally it is 6. Number of VSEPs are 6. So example BrF5. Then we'll see AB4, E2. AB4 and E2. So this shape is square planar. The square planar, it has actually 4 bond pairs, right? 1, 2, 3, 4, and 2 lone pairs. Okay, you know the angle is 90-degree. Then, okay, angle between this is 90-degree. The electron geometry is octahedral. Okay, example xenon and F4. Xenon F4 we can see. These are all the example. Okay, so for example, shapes of ammonia we saw, water molecules. Okay, so by means of I'll show you the molecules. Okay. Shapes of water molecules. See, this is the shape of water molecule. Show this molecular geometry and electron geometry. Okay, so it is for water molecule. In water molecule, the central atom is what? The central atom is O. It has 6 valence electrons, right? Hmm? You know, oxygen has 8 atomic number. So 2, 6, 6 valence electrons. 2 of them are used for the formation of bonds. Clearer? So two lone pairs are here. So remaining 4 electrons stay as lone pairs. So there are 4 VSEPs, right? 2, 3, 4. 4 VSEPs. Hence, the expected shape of the molecule is tetrahedral, we saw. So this is the way you have to learn, okay, how the molecule shape is. Okay. Then you can apply it to a real examples. Okay. So model we saw like this. Clearer? So this is real molecule. Okay. Then, but due to the presence of 2 lone pairs, the shape is distorted to bent or angular or inverted also we can say. Inverted V shape. Okay. Like this. Okay. Inverted V shape. Oxygen is here. two bond pairs. Okay, so inverted V shape, and the bond angle changes from 109 degree to 104.5 degree. See, initially, if it is inverted V shape, it is 104.5 degree. So initially it is, see, if you say, okay, 104.5 degree. Okay, so 109 degree 28 minutes or 109.5 degree is now changed into 104.5 degree. Okay, so I hope it is clear for you now. Okay, clear? Then for ammonia molecule, we'll see ammonia. Okay, for ammonia molecule, the central atom is ammonia. This blue color is ammonia. It has 5 valence electron. Right, ammonia has 5 valence electron. You know, okay, 7 out of 7 atomic number, 2 comma 5. So 5 valence electron. Among these 5 electrons, 3 are used for the formation of bonds, 3 bond pairs. So remaining 1 lone pair. So 5 is now tallied. So totally it is 4 VSEPs. 1, 2, 3, 4. 4 VSEPs. And the degree is 107 degree. Right? It is reduced now. 109 degree 28 minutes. We saw. But it is now reduced into what? 107 degree. Clear? Then here the expected shape is tetrahedral, but due to the presence of lone pair, it is trigonal bipyramidal. Okay, the shape is distorted and the angle also changes from. So these two you must notice. Okay, so what is the main point you have to understand from this? Okay, then we'll see how the orbital is overlapping. Okay, everything we'll learn right now. That is valence bond theory we are going to learn. Now we are going to see the valence bond theory. Actually, Lewis' approach only helps how to write the structure of molecules, right? So, and also the difference in bond dissociation enthalpies and bond lengths. Okay, for example, in hydrogen we saw what is the bond enthalpy? 435.8 kilojoules per mole, right? So, and what is the bond length for that? 74 picometer. Like that, so many things we have learned. So similarly, VSEPR theory gives the geometry of simple molecules, but theoretically doesn't explain them. And also it has limited applications. To overcome those application limitations, okay. Limited applications means it is having its own limitations. The two important theories based on quantum mechanical principles are introduced right now. So, in order to overcome the limitation of VSEPR theory, so what and these three theories are introduced based on quantum mechanical principles. What are the quantum mechanical principles? That is VB theory and molecular orbital theory. We can able to say, and VB theory means it is valence bond theory. Okay, actually speaking, um, so there are some very small molecules, very simple molecules are explained in VSEPR theory. What are the main limitations of VSEPR theory? You must understand. Okay, it fails to explain the shapes of isoelectronic species. Okay, so isoelectronic species means both having same electronic configuration based on, I mean, isoelectronic species. It cannot predict exact bond angles. We saw bond angles, but it is not exactly. So we saw the differences for what water molecule and for ammonia, right? So, and does not apply to transition metal complexes. Okay, and it also ignores electron delocalization and the size effects of substituent groups. Okay, these are all very important. And what are all the limitations you must know? First one we saw, it doesn't explain fully the shape of isoelectronic species. What are the isoelectronic species? The isoelectronic species means same shape to species that share an identical number of total electrons. So that is isoelectronic, that share an identical number of total electrons. So it does not work for transition metals, Visa. You are going to learn about D and F block elements. D block elements are transition metals. It controls the stereochemistry. So these and all you are going to learn in your grade 12. Then we saw it doesn't explain the exact bond angles. Then electron delocalization. That means it ignores resonance effects where electrons spread out over multiple atoms. Okay. Then inert pairs and size does not account for stereochemically active or inactive lone pairs or bulky substituent sizes. So there are so many things, complex things to discuss with. In order to overcome the limitation, there are two models are introduced. One is valence bond and another one is molecular bond, orbital theory. Okay. So valence bond theory, London, he was Hitler and London, they developed 1927 during. Okay, so further by Pauling and others, okay, it is based on quantum mechanical behavior, that is knowing of atomic orbital, electronic configurations of elements, the overlapping criteria of atomic orbitals, the hybridization of atomic orbitals, right? So the principle of superposition and variation, okay. So it is given in your book. You need to consider two hydrogen atoms, A and B, approaching each other, having nuclei Na and Nb, and electrons present in them are represented by Ea and Eb. When the two atoms are at large distance from each other, there is no interaction between them. As these two atoms approach each other, then now attractive and repulsive force begin to operate. Attractive forces arises between the nuclei and the electron, and that means you can say of its own electron. Nuclei of A to nuclei of electron, and the A. That is in an atom, it may happen. Own atom. Okay, nucleus of one atom and its own electron. So for A and B. Next one, nucleus of one atom and the electron of the other atom. Nucleus of A to electron of B, or nucleus of B to electron of A. Okay, there are two options. Similarly, repulsive forces also arises between electrons of two atoms, like E electron of A to electron of B. Nuclei of two atoms, nuclei of A to nuclei of B. So this is explained in a figure of your book. Okay, so attractive forces tends to bring the two atoms close to each other, whereas repulsive force, it pushed them apart. That also, the figure, it shows clearly. Okay. And then one potential, it is given as potential energy curve for the formation of hydrogen molecule. The energy gets released when the bond is formed between two hydrogen atoms. The hydrogen molecule is more stable than that of isolated hydrogen atom. So the energy so released is called as bond enthalpy, and it is stored as a potential energy here. Okay, so based on the intermolecular distance, the energy is varying. Everything given in your book, you just go through it. And right now, I'm going to um, explain the orbital, overlapping of orbit. Okay, orbital, how it is overlapping. So we are now going to see orbital overlap concept. So orbital overlapping, it is the process of partial interpenetration of atomic orbitals. Okay, how the orbital is overlapping, it is the partial or interpenetration of the orbitals, atomic orbitals. So the maximum characteristics of orbital overlapping are a covalent bond is formed by the overlapping of half-filled atomic orbitals present in the valence shell of atom. First point. What is the first concept you have to write in your notebook? So what is the first concept? A covalent bond is formed by the overlapping of half-filled atomic orbitals present in the valence shell of atoms. The overlapping orbital, second point, overlapping orbitals should contain electron with opposite spin. Okay. The third point, Very, very important. Electron with opposite spin. As a result of overlapping, the electrons get paired and a stable covalent bond is formed. So, fourth point is the strength of a covalent bond depends on the extent of overlapping. The greater the extent of overlapping, the stronger will be the covalent bond formed. Then you must understand the types of overlapping. So, what are all the types of overlapping? So, the types of overlapping are okay, axial overlapping. You have to understand what is axial overlapping. If the overlapping of atomic orbitals takes place along their nuclear axis, it is called axial overlapping or end-to-end overlapping. Okay, a bond formed by axial overlapping is called sigma bond. It is sigma bond. The electrons present in sigma bond are called sigma electrons. All single bonds are sigma bonds. Sigma bond can be S to S overlapping. So S orbital to S orbital. See, S orbital to S orbital. It gives S to S overlapping. Clear? Along the internuclear axis. Along the it is the internuclear axis. Clear for you? Okay. Then SP overlapping. SP overlapping means one S orbital and P orbital. Okay. So S and P. So it gives S. Draw along with me so that you can able to understand. Okay. So S and P. Or I can draw with this. Okay. Here it is. P is overlapped. Okay. S and P. It is now overlapped. So it is SP overlapping. Okay. Then these are all the axial. Okay. Then P to P overlapping also possible. P to P. Okay. Two P orbitals you can take. P plus P. It gives P. Sorry. And if the students come, I just make them leave. Okay. Ask them to leave. So yes and P. PP overlapping. Okay. P. So it is P to P overlapping. Next, we are going to see the lateral overlapping. What is the lateral overlapping? Lateral position. It is actually takes place perpendicular to the internuclear axis. Perpendicular to the internuclear axis. The bond formed as a result of lateral overlapping is called pi bond. Okay. And the electron in pi bonds are called pi electrons. Okay. See, it is lateral. Clear? Plus. This is also p orbital. P orbital. Okay. It gives lateral combination. See, lateral means both the ends are connected. Like, see, this is the overlapping. Okay. Or it may overlap like this also. Okay. It may showed. Okay. So this is the nuclear axis. It is perpendicular. Perpendicular to the nuclear axis, it may happen. It is P to P lateral opening. Overlapping. Lateral overlapping. Clearer? The pi bond is present along with sigma bonds. Double bond contains one sigma bond. You know that, right? Last year I taught you. It contains, actually it is for 11th, right? We'll see in organic chemistry. Double bond contains one sigma bond and one pi bond. Clear? A triple bond contains, if it is triple bond, single bond means always sigma bond. Okay, in covalent bonding we saw, right? Double bond means, I will explain you in organic chemistry, sigma bond and pi bond. In triple bond, how many things? A triple bond contains one sigma bond and two pi bonds. Clear? So a sigma bond is always stronger than a pi bond. This is because the extent of overlapping is greater in a sigma bond. So that's why. Okay? Clear? So then hybridization, we'll see. What is the hybridization? It is the process of intermixing atomic orbitals, having slightly different energies to form new orbitals, having equivalent energy and identical shape. So it is very important. What is meant by hybridization? Can you take this point? Hybridization. Okay, it is the process of, all of you take down. It is the process of mixing atomic orbitals, intermixing atomic orbitals having slightly different energies to form new orbitals having equivalent energy and identical shape. The new orbitals formed are called hybrid orbitals. The new orbitals formed are called hybrid orbitals. Clear? What are the characterization of the hybridization? You must know. So first characterization, better write characterization. What is the first characterization you must understand? One is the number of hybrid orbital formed is equal to the number of atomic orbitals which is undergoing hybridization. That is very important point, first point. Second point, the hybrid orbitals are always equivalent in energy and in identical shape. It should not vary. Second point. Third point, the hybrid orbitals are more effective in forming stable bonds than the pure atomic orbitals. Clear up. So in order to form the stable bonds, the hybrid orbitals are more effective than the pure orbitals, atomic orbitals. Okay. Fourth point, what is the fourth point I can say? The hybrid orbitals are directed to some fixed positions in space. It is very important. Hybrid orbitals are always directed to some fixed positions in space. Space means that interatomic space. Fixed positions in space. Okay. So the type of hybridization gives the shape of the molecule. Okay. So then what are all the important conditions you must understand? These are all the characterization. Take down this important conditions. What are all the important conditions? Okay. Conditions of hybridization. First one, the orbitals present in the valence shell of the atom are hybridized. Okay. Orbitals present in the valence shell of the atom are hybridized. Next point, orbitals undergoing hybridization should have almost equal energy, the same. The third point, the promotion of electrons is not an essential condition before hybridization. Then fourth point, completely filled orbitals of valence shell can also take part in hybridization. Okay, before that we saw only half filled in valence bond theory. Here we can say the condition is completely filled orbitals of valence shell also can take part in hybridization. First we are going to see the first hybridization, types of hybridization. So types of hybridization. So what is the types of hybridization? First one is sp3. Okay. sp3, it is the process of, we saw intermixing of one s orbital and three p orbitals. Okay. To form four new orbitals of having equivalent energy and shape. Okay. The four new orbitals formed are called sp3 hybrid orbitals. Hybrid orbitals. Clear? And I told you it is they are directed to the four corners of a regular tetrahedron. Okay, with bond angle 109 tetrahedron, 109.5 degree. Okay, wow. So I'll show you that molecule and everything. So each sp3 hybrid orbitals has especially 25 percentage s orbital, s character, and 75 percentage p character. You know, right? 1:3. Okay. Then Example. With the example, I will explain you. First example is CH4. How the molecule of methane is formed. You know, carbon. Okay, so carbon has 6 electron. Okay, the central atom C has the electronic configuration. How we can write the central atom? Central atoms electronic configuration. What is that? 1s2, 2s2, 2p6. So the valence is like this. How can I represent the orbital? 1s2, okay, 2s2, then 2p4 here, right? So how it is formed? 2pex, 2py, and 2pz. 1, 2, 3, single occupied. The fourth one comes to the, sorry, 1 is to 2 is 2p2, right? For carbon only we are talking about. Okay, 2p2. So this, in this orbital, it should have, okay, 2px1, 2py1. Okay, so there are two lone pairs, right? In order to explain the tetravalency, it is having tetravalency, right? So 2 plus 2, it is having tetravalency. Tetra means 4. Okay, it is suggested that one of the electron is 2s, right? Promoted to 2p orbital. Okay, see how it is formed, excited state. Okay, so what is the excited state? So here, one of the 2s electron, okay, electrons of 2s orbital, it is shifted to this empty orbital. Okay, clear? So one s orbital and 3 p orbitals undergo sp3 hybridization now. Okay, one s orbital and 3 p orbitals. These sp3 hybridized orbitals are directed to the four corners of regular tetrahedron with bond angle 109 degree, 109.5 degree. So each of these sp3 hybrid orbitals overlap with 1s orbital of hydrogen to form C2H, C2H like that. I mean, sigma bond. Okay, let me show you that. Actually, carbon, how the carbon is arranged. On the plane, it will be 2 hydrogen, then solid wedged line. So I can draw a solid wedged line. Okay, here. Okay, then here also one hydrogen and another hydrogen